An example of this mechanism is alpha halogenation. It's a common alpha substitution reaction that occurs in an acid catalyst. So here's our general reaction. If I have a ketone like this that has to have at least one alpha hydrogen, if I react it with a halogen in acetic acid, I can do a substitution reaction. So we went from acetophenone, right, benzene C double bond O CH3, to alpha bromo acetophenone. And this is sort of a little more casual nomenclature, but it's still accepted. If we have something substituted next to a ketone or next to a carbonyl, we can refer to that as alpha bromo or alpha methyl or whatever it is. So we did a substitution at the alpha carbon. This was an alpha bromination. So let's look at this mechanism. It's exactly what we just did. The carbonyl first tautomerizes with the acid catalyst that's present. And I mean, this says HBr. It would be a little more realistic if we called that HAC for acetic acid. So we have protonated the carbonyl. We'll have whatever that was, whatever the conjugate base was of that, to remove the alpha hydrogen then to make the enol. Right? So that could be acetate, for instance, or it could be water. So here's our plain old regular enol. Then it does what we said it does. On the enol, the oxygen donates its electrons in. That causes the CC pi bond to attack an electrophile. And when I have Br2, one of the bromines acts as an electrophile. We saw that first semester when alkenes attacked bromine to make a bromonium ion or something like that. So if I have a halogen, right, Br2 or Cl2 or I2 or something like that, one of those can act as an electrophile because the Br electrons go onto the other halogen, making Br minus. So with every equivalent of bromine that I added, I make one equivalent of bromide of Br minus. What happens then is we have this protonated carbonyl. It's alpha bromo now, but conjugate base attacks that oxygen hydrogen, right? It deprotonates the O, right? So that could, for instance, be bromide. That forms HBr, which can act in up here as our original catalyst, or we could have acetic acid, right? So down in here, we reform acetic acid. Down here, we reform HBr. So it really uses catalytic acid, but does it twice in this mechanism. So we could just call that HBr or HAC, right? This base could be water, it could be bromide. I guess it's not entirely crucial that we account for exactly which acid is making protonation happen or exactly which base is removing a hydrogen, because it's some mixture. They're sort of all doing it. So if you want to even put base with a little lone pair on it in your mechanism, that's acceptable if there's multiple possible bases that could be doing it. I probably wouldn't complain about that. So as a way to confirm the fact that it's the enol that actually reacts and not something else, is if we use a different electrophile. If I had just a regular ketone and I reacted it with D3O+, right? That's the deuterium version of hydronium. That's catalytic deuterium acid. We get the exact same rate of reaction as we would with really any other electrophile. So that's evidence that rate is not dependent on the electrophile, that the slow step is the enol formation. So these reactions always occur via the enol intermediate. And then as soon as some little bit of enol is formed, that enol rapidly reacts from the alpha carbon going out and attacking an electrophile to do the substitution. So if we have really any carbonyl and we put it in D3O+, we'll substitute deuterium in at the alpha position. So that can sometimes be useful, for instance, in NMR, because deuterium does not show up on NMR. If you want to simplify your spectrum, if you got a whole big mess of peaks or something, you can react it with a little deuterium and acid and get rid of some alpha hydrogens, for instance. Another useful thing about this reaction is that if I have a ketone, like this for instance, I can do Br2 in acetic acid. I do an alpha brominated ketone. Then if I react that with some sort of base and heat, I can eliminate. I can do an elimination to make an alpha-beta unsaturated ketone. That is by an E2 mechanism, because if I look here, there's at least one hydrogen on the beta carbon. What we do here is our base attacks a beta hydrogen. That makes a CC double bond, and it kicks out the halogen that we've added in the alpha position. So E2 reaction happens all at once, where we attack a hydrogen, that makes a double bond, and then that kicks out the leaving group next to it. So that's actually probably the best way of forming alpha-beta unsaturated ketones. And as we've seen before, that's how you can go in and add something to the beta position, right? Right here in this chapter, we're talking about just how to directly add something to the alpha position. But to add something to the beta position, first, alpha halogenate, eliminate it to make the alpha-beta unsaturated, which then can be attacked. The beta position is electrophilic, so a nucleophile can attack it. If I have an acid-catalyzed alpha substitution reaction, that'll tend to occur at the more substituted position, because that comes from the more stable enol intermediate. If we look, we have 2-methyl cyclohexanone here. There are 2 possible enols that we could make out of it. We could make the less substituted enol, where the double bond's going away from the methyl, or the more substituted enol. Just like that. Okay? The one where the double bond is more substituted, right? This is a tetra-substituted double bond, whereas this one was only tri-substituted. This one is a more stable intermediate, and that means that'll make the pathway with this one faster, because it'll be less energy required to get to this intermediate, which will then go on and react. Okay? So if we're acid catalyzed, we're reacting via an enol, so that'll essentially be by, what was it called? Zaitsev's rule, where we have the more substituted double bond being the more stable one.